We discussed the persona pattern and how we can use it to give the large language model all of this rich information about what it's supposed to do and what it's supposed to output with a very little bit of work on our part. All we have to say is act as, and it will know what it's supposed to do and how it's supposed to format it and the types of things that it's supposed to incorporate into its output. Now, sometimes what we'd also like to do is we'd like to do the same thing, but rather than focusing on who the large language model is supposed to act like, we want to have the large language model produce an output for a particular persona. So this is called the audience persona pattern. The idea behind this is we want to tell the large language model, you need to produce an output for this audience persona, for this person or thing, so that it can think about how to tailor the output. And it will use its knowledge of the audience to make sure that it generates an output that is appropriate for that audience. So rather than saying you don't do this or having a whole bunch of different rules describing what is and is not okay to go into the output, instead we say this is the audience of your output. This is the audience persona. And so with the audience persona pattern, we can get a similar type of reasoning and ability out of that we got from the act as this persona, using the persona pattern. We can get that by saying, here's who you're providing the output to. This is the persona of the audience in order to get interesting outputs. So let me show you an example of this. So we're going to start with the example of large language models, which we've been studying in this course. And we're going to say, explain large language models and how they work to me. Assume that I have no background in computer science. So we're giving it a persona of who I am. We're saying, assume that I have no background in computer science, and that's telling it who is the persona, who is the audience that I'm giving this information to. And so it says, sure, let's start with the basics. And I want to call out just a couple of things. It starts with a very sort of, intuitive way of describing this. A large language model is a type of computer program that's designed to understand and generate human language. It's a bit like a virtual writer that can understand and create sentences in a way that sounds natural to humans. And so it's not describing it like it would to a computer scientist. It's describing it to be, something that is accessible and approachable to anyone. Language models are used in many applications such as speech recognition, machine translation, and chatbots. Now let's talk about large language models. The word large refers to the size of the language model, and it goes on to describe it, and it says parameters are like adjustable knobs that the model uses to learn patterns in the language. So it's describing what a parameter is in a sort of accessible way. And it goes on and it talks about all the different steps in creating this. So it did a good job, right? I said, assume that I'm not, I don't have background in computer science, and explain it to me. And so it made sure in its explanation that it had the right information and then presented it at the right level for me. So let's go a step further. Let's show you how interesting this can get. I'm going to say, explain large language models and how they work to me. Assume that I am Christopher Columbus. So notice, now I'm giving it something completely different. I don't know how you would explain large language models to Christopher Columbus. So it's going to have to use and draw on information in its training data and patterns related to Christopher Columbus and history to try to figure this out, right? I'm giving it an audience persona that's a tricky one that I wouldn't know how to do easily. And it says, greetings, Christopher Columbus. As an explorer of 15th and 16th centuries, you may not be familiar with the concepts of computer science and artificial intelligence. And I don't know how well this really works, but it's still pretty good that it's doing it. I'll do my best to explain it. Imagine that you have a magical scribe, a being that can read, write, and understand many languages. This scribe has spent years reading countless books, scrolls, and manuscripts from all over the world. It has learned from poets, scholars, and storytellers. The magical scribe has a special ability. It can predict what comes next in a sentence. For example, if you say to the scribe, the ocean is vast, it might respond with mysterious, completing your sentence in a way that makes sense. And so you can see how all we did is we said, you're going to explain the exact same thing, But you're going to assume in the first case that I don't have knowledge of computer science. And then we said, now you're going to assume that I'm Christopher Columbus, right? And so it completely changes how it describes large language models. And it's actually doing a pretty good job. So it's saying here, like Christopher Columbus doesn't know what a computer is. Christopher Columbus, but maybe this concept of a magical scribe, right? And a magical scribe could be a concept that could make sense to Christopher Columbus. And then he's explaining how large language models predict the next word. He's saying the magical scribe studied all of these, these scrolls and poems and different things and learned to figure out what is the next word in a sentence. And now we're going to use that magical scribe, and we're going to talk to the magical scribe. So he's explaining, the scribe like Christopher Columbus, as he's going to understand it. As Christopher Columbus will be able to look at the text and kind of understand that, like, okay, I have this large language model, and now I've got this magical scribe. It kind of makes sense on what that means and like how that would possibly work. So now let's look at a third example. We say, explain large language models and how they work to me. Assume that I'm a second grader that gets bored easily. And so again, we're given a totally new persona, and we're also refining this persona. We're saying I'm a second grader, and here's some additional details about me. I get bored easily. And so now it goes and says, okay, I'm going to tell you something super cool called a large language model. Imagine having a robot friend who's really good at playing word games. This robot can finish your sentences, answer questions, and even tell you stories. Here's how it works. Reading time. The robot friend loves to read. It reads lots and lots of books, websites, and all kinds of things with words. And so it's explaining this concept of, similar to as it explained to Christopher Columbus, it told Christopher Columbus, the large language model is like a scribe that's read all of these scrolls and poems and things like that. And now the large language model is explaining to the second grader, it's like a robot. And the robot loves to read. It reads books, websites, and words. And so now it's switched up the description based on the persona of the audience. And then it goes on to describe all of the different aspects. Again, and you could go through and ask it, to describe it in many different ways. So if we wanted to go back and we wanted to say, well, let's switch it up from a second grader, and let's say, assume that I only accept explanations in math. And then we could say something completely different. So now it's saying, okay, language model is a probability distribution, and it's trying to give a mathematical explanation of what a large language model is. And we can see that we're getting something completely different. And each time, we don't have to necessarily think through, well, how would I explain this to Christopher Columbus? What would the rules be to describe how that output should look? We don't have to tell it what the output should look like. We tell it who the audience is, the persona of the audience, and then we get all of that rich capability around it. So just like the persona pattern is really useful in tapping into large language model capabilities, the audience persona pattern is sort of the complement to it, and is also sort of an equally powerful thing that we can use to basically get really interesting and powerful output out of large language models. You may remember being told to show your work when you were a student, probably in elementary school or middle school, and you were working on a math exam, and you had to explain how you got there. Or maybe if you've gone on and you've done other things where you had to prove, that something was true that you had decided. And so showing your work, explaining your reasoning is something that can be really important in a number of different domains. And it turns out that when it comes to writing prompts, this can be really, really important. Getting an LLM or a large language model to explain its reasoning behind something actually can make the large language model perform better for us. Now, this is a really interesting thing, but if you think about it, it kind of makes sense, right? Because we have a large language model that's trained on different patterns of text. and it's learned to predict what comes next. So if it can explain its reasoning correctly, then it's more likely that it's then going to produce the right answer, because the right answer sort of intuitively should come after the correct reasoning. Similarly, if you think about it, if it starts explaining the reasoning correctly, if it gets the first step right, it's probably going to get the second step right, because it may have seen similar problems reasoned out. Now, this is an intuitive explanation. This may not be right, but I think intuitively you can kind of think about it is that if you break down the problem you're solving into multiple independent steps and you explain them and there's sort of a natural sequence and logic and flow to them, it's more likely that the final output, which is the answer, is going to be a natural extension of the correct reasoning and therefore correct. It's more likely to be correct if your goal is to accurately predict the next token. Similarly, if you have the problem and you get the first step right and the second step right, you're probably going to get the third and the fourth as a large language model because you've been trained on this stuff. So there is a technique for this, and it's called chain of thought prompting, and I'm going to show you examples of this. But it's really helpful to remember when you're building prompts that require some sophisticated sort of intelligence and reasoning capabilities. Now, we don't always need this type of breaking the process down step by step and explaining the process. But when we do, and we need that more effective reasoning, it's really useful to understand how chain of thought prompting works. So I'm going to start off with a positive example where we use it and we show what it does and how it works. So we have some examples here that we are going to give. Sorry, I'm actually going to start off with the negative example first. I apologize, that was a mistake. So I'm going to start off an example that does not use chain of thought prompting, and I'm also going to show an example where I'm going to make a mistake in how I phrase the prompt and how I structure the prompt. And I'll come back to this mistake in a second. But what I've got here is I have three different questions that require some reasoning. In the first two, I've given an example of what I want. I say, I have 4 bike racers start a race and travel an average of 30 miles per hour. They each race for 2 hours. Is the total number of miles ridden by all riders greater than 200? And then I have an example and I say answer yes. And then I say a question. I have a staging process for a bike race to line up racers. It takes 47 seconds to stage a group of 8 riders and 67 seconds to get the group to the starting gate and ready to race. I want a new group to start the race every 30 seconds. Do I need 8 groups staged at all times in order to have races continually starting every 30 seconds? And the answer is no. This is the example I'm giving it. And we'll see the reasoning behind these in a minute. And then I say, I am in a spaceship without gravity. I have a cup with a needle in it. I move my foot on the bed, knocking over the cup onto the floor. I lift a book up and put it on a desk. Is there anything on the floor? Now, this is the question I'm trying to get ChatGPT to answer. And so I've given it basically some examples of questions with answers of either yes or no. So I'm trying to elicit a yes or no answer from ChatGPT. I'm using few shot examples to do that. And I'm showing it questions, I'm showing it answers. And then I'm asking it for the answer about this question about a cup knocked on the floor. Now, I have actually seen some variations of this, and I apologize because I don't remember exactly where I saw this first example of reasoning with the cup and the needle inside of it knocked on the floor. But I thought this was an interesting one because it works really well for showing the difference between chain of thought prompting and without. So this is without chain of thought prompting. So what does ChatGPT say? Because we asked it, is there anything on the floor? So the question was, I'm in a spaceship without gravity. I have a needle with a cup, or I have a cup with a needle in it. I move my foot on the bed, knocking over the cup onto the floor. And then I have some irrelevant information. And then I say, is anything on the floor? Now, without chain of thought prompting, it says yes. When the cup with the needle in it is knocked over onto the floor, both the cup and the needle will end up on the floor. In the absence of gravity, objects will not fall downward as they do on Earth, but they will still move in response to forces applied to them. In this case, the force applied by your foot knocking over the cup will cause the cup and the needle to move and come to rest on the floor. Lifting a book and putting it on a desk does not affect the position of the cup, so they will remain on the floor. So it says, yes, there's going to be something on the floor, the cup and the needle. Now, let's look at the same example but with chain of thought prompting applied. So here we go with chain of thought prompting. So with this one, we've spelled out the reasoning behind each of the examples. So we go back to the bike racer, and we say, will the total be greater than 200? And so we say reasoning. Each rider will ride 30 miles per hour times 2 hours equals 60 miles. I have 4 riders. Therefore, the total number of miles ridden by the riders is 4 times 60 miles equals 240 miles. And then answer yes. This is chain of thought prompting. We're explaining the reasoning behind the examples to the large language model. So in this case, we're sort of working out the math, showing our notes of how we got to this answer. And then we do the same thing for the next one, where we're staging a bike race and we want to figure out how many people have to be staged at a time in order to start a race every 30 seconds. And we give the reasoning. Each group takes 47 seconds plus 67 seconds to be ready to race. So I will need to calculate how many races will need to be run before a group is ready to race. A group will have 114 seconds over 30 seconds equals 3.8 races run before it is ready to race. I can't have a partial group, so I need to round up to 4. I only need 4 groups staged to be able to race every 30 seconds, so I do not need 8 groups. Answer, no. And so you see, rather than just say, here's the example, here's the answer, we say, here's the answer, here's the reasoning, and then here's the answer, the correct answer. So then in this final example with the spaceship, again, we're having the spaceship, there's no gravity, we have a cup with a needle in it knocked on the floor, and then in this example, we tell it to provide its reasoning first, and then its answer. So we're prompting it and giving it a format that makes it clear we want the reasoning first and then the answer. And what's interesting is we see different reasoning than we saw before, and we get a different answer. If you remember before, we got the answer of yes, their cup and the needle will be on the floor. But if you look down here on this one at the bottom, we can see that it says answer no, because there's no concept of on the floor in a zero gravity environment. So if we look at this one's actually giving us sort of a better reasoned answer in my opinion. Now there's probably different nuances, and I'm not an expert on this, but I think if you don't have gravity, you're not necessarily going to have the cup and the needle resting on the floor just because they got knocked off. And so the reasoning is better. In this one it says, in a spaceship without gravity, objects do not behave as they do on Earth with gravity. When the cup and the needle is knocked over, the cup and needle will not fall to the floor as they would on Earth. Instead, they will float in place or move in the direction of the force applied to them. And so, therefore, in the absence of gravity, there is no concept of objects being on the floor as we stand them on Earth. And so basically what it's saying is like, well, you might move them or cause a force to be applied, but they're not going to just sit there on the floor because there's no gravity. And so it comes up with the answer no. So you see right here, we're getting a completely different answer out of the large language model. And the difference is that one example, we're giving it the examples, we're giving it the reasoning behind the examples, and then we're asking it to provide the reasoning and then the answer, which is this case, and where we're saying no, there's nothing on the floor, which is probably a better answer in this case. In the other example, all we're doing is saying, here's the question, here's the answer. Here's a question, here's the answer. And we're not giving it the reasoning. And then finally we're saying, here's a question, and it's going to try to produce the answer first, which is what it does. And so the difference is really only in what it does. Here it's answering first, but it's not explaining its reasoning first. And its reasoning actually isn't quite as good, and its answer isn't quite as good. Now, spaceship, knocking a cup with a needle off on it, this might not apply to you, but it's an interesting example of where there's more nuanced reasoning. And if you have a case where you need to have it think through, and I say think very liberally here, but if you need it to try to get better reasoning behind the answer, or a better computation, whatever you want to describe it as. But intuitively, if we've thought through the process of getting the answer, and we have a good process of breaking down the problem and going step by step to a solution, we're likely to get a better answer out, a better solution out. And so that's what chain of thought prompting is doing, is we're trying to elicit that that break the problem down into steps. Think about, step by step how you're going to solve it. And the way that we get there, the way that we get to do that is when we give it few shot examples like we do up here, we explain the reasoning behind the answer, and we explain the reasoning first. We say, this is what I'm thinking and doing. This is why I'm getting there. Similarly, we do it on this one too. We say, here's my reasoning, and we provide the reasoning before the answer. And the goal is to get the large language model to do the same thing, to follow our pattern of breaking down and explaining the reasoning before giving the answer, to think through the problem, to give the fundamental steps, and then to produce the answer. And we get better outputs in this case, and in most cases it's been shown that you're going to get a better reasoning out of the large language model if you have it explain its chain of thought, what it's thinking through, what it's trying to do in order to solve the problem. Then you'll get a better answer out. Describing everything in full English sentences or full sentences in whatever language you speak isn't always the easiest way to give the input to the large language model. Now, if you think about it in the real world, a lot of times we have our own specialized languages to describe different domains. So math may have its own specialized language, or we may have shorthand for taking notes or describing different interesting things. We may create our own little languages to be able to capture information in a more concise way than if we wrote it out in full sentences. Now, of course, the key to these languages is that the person that we're communicating with in the language knows the language too. They know the meaning of the different the statements that we're making, the different symbols or words that we're using. Now, as an example of this, we've been doing a lot of work in partnership with the city of Nashville and the emergency responders. And one of the things they do is the operators who are taking calls, and you can imagine this is a really stressful situation. They're trying to take notes down about what's going on in an emergency, and they actually have their own shorthand notation. You can imagine the stress and difficulty of receiving a call around an emergency and trying to take down information that can then be used to, take the appropriate action, send an ambulance or send a fire truck or whatever needs to be done. And so they have their own little shorthand notation. And if you go and just try to read this, you're not necessarily going to be able to read it and understand it, because it's designed for people who use it day in and day out to be able to communicate with each other, but not necessarily to be as explicit and obvious as possible. So I'm going to teach you a pattern where we can basically teach a large language model a new language and then communicate with the large language model in that new language or shorthand. So this is called the meta language creation pattern. So we're going to create a language. This is going to be our meta language creation, where we're going to go and describe to the large language model what our language is, what are the meanings of different symbols or statements in that language, and then we're going to go and converse with the large language model using it. So let's look at our example here. We're going to create a trip planning application. Now, I haven't gotten into the meta language creation pattern, but I'm giving you an example that uses it. So we're going to create this trip planning application. I will describe my trip, and you will list interesting things to do in the places that I will pass through. I will tell you how many days I will stay in each place, and you will list possible itineraries. So far, we've just got a prompt to help us do trip planning. Now, here's where we're going to go and use the meta language creation pattern. I'm going to say to describe my trip, my route, I'm going to use a shorthand notation. So we're cueing it in, and we're going to tell it about this shorthand notation. When I say, and notice this, Nashville, 3, arrow, Memphis, 2, I mean that my route will go from Nashville to Memphis, and that I will stay 3 days in Nashville and 2 days in Memphis. Now, I want to kind of draw your attention to something here. Notice that I'm starting off by saying, when I say this, here's an example of my new language that I'm creating, or my new shorthand that I'm creating. I mean this. And so you're taking an example and then you're showing it what you mean. So you're then saying, I mean that my route will go from Nashville to Memphis, and I will stay 3 days in Nashville and 2 days in Memphis. So you're giving it basically a translation. Now, another way to think about it, this is similar to few-shot examples. You're saying, here's an example of, input, here's the example of the output, or here's the example of a comment on a movie, here's an example of the sentiment analysis for that comment. You're kind of doing something similar, except what you're doing is you're saying, when I say this in my language, this is what I mean, and you're showing it the translation and the meaning behind it. The other thing to note is that my notation is much denser than the full English that I'm going to use. So it's Nashville, 3, arrow, Memphis, 2, and it's that short thing is describing this much longer basically statement that says my route will go from Nashville to Memphis, and I will stay 3 days in Nashville and 2 days in Memphis. I could write all this out, but I want to have my notation. Now it goes ahead and trip plans for me on Nashville and Memphis, and I'm going to skip that, and I'm going to go down to now where I have an actual just statement. So notice we've now programmed our new language. We've done the meta-language creation pattern, and now the large language model understands our language. So we say Nashville, 0, and Nashville, 0 means I'm leaving from Nashville. I'm not going to stay there. I don't want you to trip plan for me in Nashville, which is an interesting thing that has to, consider that in the logic. I'm going to Dallas, 1, and then arrow Granbury, Texas, 4. And so basically what I'm saying is my trip is going to go from Nashville. I'm not going to stay there at all. Dallas, I'm going to stay there 1 day, and then I'm going to stay in Granbury, Texas for 4 days. And it says, sure, since you mentioned that you won't be spending any time in Nashville, I'll focus on providing you interesting things to do and possible itineraries for your 1 day stay in Dallas and your 4 day stay in Granbury, Texas. So it then plans our 1 day stay in Dallas. We have a 1 day stay in Dallas. It describes what we're going to do on that day. It then describes for Granbury, Texas over here. It says 4 days, and then it describes what we're going to do in Granbury for the 4 days. Now, if I wanted to experiment with different itineraries and I wanted to really quickly have a shorthand for saying, well, what if I did this itinerary? What would I do? What if I did this one? It's a lot more condensed. Now, also, I have to admit, I'm a computer scientist and a programmer, right? So I like having things that look like condensed programming language instructions, but you can imagine a lot of people use shorthand notation abbreviations. You can use them too in the language model. You just have to explain it to it, unless it already knows it. If you're using something that's well understood, you can just say, I'm going to use this language, or I want you to interpret this in the same way that you would interpret it in a math context, and you could explain what that means. So it plans our trip. Then here's where I go and try it again. Look, I'm getting a more complex statement. I'm saying I'm going from Nashville to Fairhope, Alabama, where I'm going to stay 3 days, to Gulf Shores, Alabama, where I'm going to stay 1 day, to Montrose, Alabama, where I'm going to stay 1 day. So now I've got a much longer statement, and if I had to write that all out in words, in full sentences, it would take a lot longer to write it out in full sentences. But I've described the language, and now this kind of crazy string that I've put together, it knows to take that and use it as the input for the trip planning. So now it says Fairhope, Alabama, 3 days, and it gives me my planning for my itinerary there. So it gives me my day 1, day 2, and day 3. It then says Gulf Shores, Alabama, 1 day, and then it provides my itinerary for that 1 day in Gulf Shores, and then it understands Montrose, Alabama, and gives me my 1 day stay in Montrose and gives me examples of things to do. So you can imagine that this is a really sort of helpful capability. You may want to go and start thinking about, how do I develop a shorthand notation for the tasks that I do really frequently with the large language model, and where it would save me a lot of time and effort if I could describe what I want using some shorthand, and maybe we can also describe it more precisely. Maybe there's a way to describe it more consistently. So if everybody uses the shorthand, the meaning is less ambiguous because we've already defined it in advance, and there's less variability in the explanation, or in the how you express it in the shorthand. So maybe you're an organization and you want everybody to express certain information the same way to make sure that the reasoning from the underlying large language model is consistent. And so Now, it's not always necessarily going to be consistent, but at least you would get the data, entered in a more consistent way. So you could define your own language for your organization for describing certain types of information and teach that to your people so that when they go in and they enter in that information, you're going to have a consistent sort of semantics to what that information means. Now, if everybody goes and just describes it in English using whatever phrasing, whatever level of detail, etc., that they want, you may not get the outcomes you want from your prompt. So by having your own language or shorthand, you can help constrain how you define things, how you express information to the large language model, and hopefully help it reason better. When we're working with computer software, one of the things that's really useful is that programs typically have some menu with a series of actions that we can apply. So if you've ever used word processing software, there'll be like a file menu that allows you to run an action to open a new file or save a file. You may have a menu that allows you to search and replace different pieces of text. So this idea of having a menu and different actions that we can run is a really useful concept. And sometimes when we're working with prompts and prompt engineering, and particularly when we have a long conversation, it can be helpful to sort of develop the equivalent within a prompt. Basically define a set of, essentially a set of actions that we can run in order to work in the conversation without having to repeat these long prompts. Or we want to just sort of codify certain actions that are helpful to people and bake them into a prompt at the very beginning of the conversation. So let me give you an example of this. We're going to look at using the menu actions pattern. This is a pattern that allows us to get the same type of behavior but in prompts. So we're going to develop a menu that is a series of actions that we can run, and actions are basically, essentially a prompt. It's basically a set of instructions that we're going to give the large language model in order to do something at a particular point in the conversation. So here is how this works. We describe what we're going to type in order to trigger the action. So I say, whenever I type write bullet point paragraphs, and let me talk about this in more detail in a minute. So don't worry if this seems just doesn't quite make sense yet. So whenever I type this phrase, write, and then I have in less than, greater than, bullet point, and then paragraphs, these are placeholders. So basically I'm saying I'm going to type in write, and then a placeholder for a bullet point, and then a placeholder for a number of paragraphs. You will write content for the selected bullet point. So basically what I'm saying is I'm going to give you a bullet point that you need to go and write the content for. And then I'm going to tell you how many paragraphs of text to write. And then you're going to go and write the text. So basically I'm developing an action which is, before all I could do was expand my outline. So when I talked about the outline expansion pattern, I talked about being able to rapidly expand the outline. And now what I'm going to say is at some point I'm going to be able to tell you, no, go and turn that into text rather than just outline. So I'm creating a new action. I'm also going to go ahead and keep my original action, which is just expanding the outline. So I say whenever I type and I have a placeholder for bullet point, you will expand that bullet point. So what I'm saying is if I just type in like 3.5.2, which is a bullet point, like a number in my outline, it'll know that it means expand that in the outline. If I instead say write, which is kind of a keyword, and then a bullet point and a number of paragraphs, it knows that that means it's supposed to write the text for it. So I'm defining a menu. I now have two actions. I can either expand my outline or I can write the text for part of my outline. And so now I'm developing more sophisticated capabilities for my outline expander. I'm turning it into a real program now, something that I can interact with. So let me show you an example. Now here's my first action being run. I'm saying write 3.5.3 to. Now what that means is write the content for the bullet point that was labeled 3.5.3, so label 3.5.3, you're going to write the text for it, or for that part of the section in the outline, and you're going to write 2 paragraphs. And so what we see is it takes the bullet point 3.5.3 from the outline, which was experimenting with tone and style variations. It then writes 2 paragraphs of text for that bullet point. So I've created an action, I've defined it, and I've created a menu of actions and I've defined it in my prompt, and now I can run that action and get the text generated. And so then we see it prompts us again, what do we want to do next? So this is actually not part of the text it wrote. So it did write 2 paragraphs, then asked me what I want it to do next. So then now I'm going to go back and I'm going to do exactly what I did before. I'm going to say expand on 3.5.2. So this is what I did before, and now it knows the difference, and it knows that's a different action. And so it goes and expands 3.5.2 and puts the outline for it again. I then go down and I say, okay, give me text for 3.5.2. And notice something kind of interesting. I'm actually making a typo here, but it's kind of being smart and inferring what I'm supposed to do. And this is kind of an interesting thing, is it's a very sort of, it tries to help you out, tries to get things right. And it knows based on the pattern that what I probably meant was write 3.5.2. Instead I wrote text. So it's kind of a smart menu action system. And then it actually goes and it pulls in that bullet point, 3.5.2.3. Sorry, I said that wrong. It's 3.5.2.3. And then it writes 1 paragraph of text. And so I've created basically a complex program where I can expand my outline if I want to, or I can have it write the text for a part of the outline, but I don't have to repeat myself. I get to use this simple little format, and I've explained what the format is, and now I can rerun the actions whenever I want to. So one way this is useful to me is, like, if you're doing the same task over and over with prompts, it can be helpful to use the menu actions pattern to basically define a set of actions on kind of like on a menu of a prompt that you use all the time. And then whenever you want to iterate really quickly using that content and those set of actions, you can just introduce that menu actions prompt and then go and use those actions over and over on the output that you're getting in order to manipulate it or do something. You've basically built yourself your own program within the conversation. At the same time, sometimes an organization may have, a number of people that are doing the same job, and they can share actions with each other to help automate different tasks. And so this could be really useful to help people be more effective with their jobs and to share with each other useful prompts. The other thing is you don't have to worry so much about remembering exactly how you worded it, right? Once you've written the action once and gotten it to work in the menu, then you can reuse it over and over without worrying about, not quite getting it right when you do it. And then that leads into a final thing that's really useful about the menu actions pattern, is that within an organization, you can share a set of common menu actions that everybody should use, and you can codify the best, wording for those prompts and for those actions and what they should do, maybe codify best practices into them, and then share them across the organization. So it allows for knowledge sharing and reuse of different prompts, and then easy application of those prompts. You could also imagine baking these into a root prompt for something like a customer service portal where you want to give people certain actions they can run to look up information about their account. They could do it in natural language, but you could also describe, here are some actions you could run, and allow them to get better behavior out of it. So the menu actions pattern is a really powerful pattern that allows us to easily reuse other prompts and actions that we've used to share them with others and develop knowledge bases of them so that we can become more effective prompt engineers.